Oh, hi. Yes.
Oh, wow.
Okay.
Is it working?
Yeah, if it's not working for people to, but it looks like it's working, so it should be fine. I will also leave this open if someone sends in a question of some sort.
But I don't want to have to monitor the channel.
No.
Okay.
No. Maybe at the end I can come here actually and monitor.
Yeah, in the end, yes, I might take it. There will be no end. So
Mm. All right.
So I will just check the camera. So. Yeah, should be fine. So, I don't know how to behave properly with or without mask. I will be talking a lot. I think so. And I might be a spreader because my wife is vaccinating people about 200 a day. And I'm close to my wife. And so.
Now it's too late.
It's never too late. So I will try to leave this mask on. And if it's too inconvenient for me, I will ask you whether I can take it off. Okay? So, yeah, I didn't prepare any slides. I have high gloss slides on all the stuff that I'm now talking about, but I want this to be more interactive and not just give one of these standard presentations. So I was asked, I don't actually know exactly what I'm supposed to talk about. I heard keywords that sort of made me snap after the debate. One keyword is CogniGron. This is an interdisciplinary research center, which I think is not widely enough known among students what they do, who they are, what they want. And the other is more scientific. What kind of research are they doing there at large in CogniGron, and maybe what research can I personally, so my group, contribute to it? So these are three topics: CogniGron, institution. I will just explain it briefly, how it came about, what it is, and what Groningen wants to achieve with this thing. And okay, so I will just start with that, and then the research mission generally, and the difficulties, because it's more difficult than anyone can imagine. And I will explain this. Yeah, and if there's time, what I'm doing, but I think that's the least, I should say, the least important. Okay, so CogniGron. Yeah, I like to use real chalk. I don't want to sort of snap this into a flat screen, that would be. Your medium. So now you and the camera can both see something. Okay, CogniGron. So it's, I don't know whether it's an institute, a center, an initiative, or whatever. It's the CogniGron Groningen Center for Cognitive Computing, or Computing and Cognitive Materials, or something. So we will come later to how confusing all of this is. So it's, first of all, it's an initiative between two institutes, the Bernoulli Institute and the Zernike Institute. Zernike is our biggest institute that we have on this campus, and I think when I came freshly here, they told me it's certainly Europe's finest materials research institute, including a Nobel Prize winner, and maybe the world's best. So no, that's just their modest way of seeing themselves. No, and I think as far as I can see, they're right. So I have been visiting a number of other material research centers in the last few years, and this is with some enormously visible distance, by far the biggest and best funded. So there are about 40 groups. It's huge. They fill this Zernike building, which now they get rebuilt in a bigger one. It's all physics, chemistry, and especially material science. So material science is the driver of this. Material science means that people from chemistry, physics, engineering try to find new materials, stuff. And they find and want to find new materials. They hard coats on somewhere that reflect sun, that can transfer sunlight into electricity at cheap costs, that are good additives or enzymes or whatever to help other chemical processes. So it's a very large diversity of things that are being done in material science, because everything is made out of materials in the end. So you can see, you can imagine that this is a very wide field. But now it happens that there is a new fashion in material sciences. And this new fashion is that they want to produce materials that can compute. Not transistors that you can wire up to have the digital circuits, but they always see my belly. So. So the materials that compute, there is a classical line of materials research into computing devices, transistors, diodes, and so forth, where they just try to make better transistors and diodes and all of this and so forth. But there is a more innovative brand of material science who try to build crazy, entirely new, strange, nanoscale, microfiber, super nonlinear, brain-like materials that can compute in ways that are totally different from what happens on those machines, and that are much more brain-inspired and closer to what happens here. Because we don't have copper wires and we don't have transistors, we don't have bits in our head, something else we have. And this works much better than any AI system that we have so far. And there's an incentive, I will say more about this, why this incentive is currently so strong. There's an enormous incentive to study alternative ways to computing that are not based on the way that we know it, with digital computers and bits and programs and ultimately the Turing machine and all the things that you may learn in theoretical computer science. There is no name for this more generalized way of doing computing that people dream of. There is actually a flood of names that has been proposed. I have a private list of about 25 names that have been tried to be people who first proposed and tried to brand them and become connected to these names. Currently, the most popular name is Neuromorphic Computing. So I will just write this down, but it's not the only. So if you hear neuromorphic, I will just write it down. Neuromorphic. C always means computing. So, but there are other, likewise, fairly widely spread names for this way of thinking, but certainly more respectable or old-fashioned is unconventional computing. Or immaterial computing, or material computing, or physics-based computing. I will just write down one of these. Immaterial computing. Here the naming tries to suggest that in order to have fundamentally new ways of doing computing, you must start with materials. If you want to understand the brain, you shouldn't do this abstractly. Do not start from a brain Turing machine model, but look at what does brain physiology give you, the physical basis. And the physical basis enables and disables certain things. And then if you have an understanding of that, build your theory of computing. That's one of the ideas behind, if people use this word, immaterial computing, that they start not from computational principles and then see by what machines and devices can we realize them, but they start from the physics and then want to see what can we do with these strange physics. So it's a different way of, different direction. Material computing, well, and more. Physics computing, natural computing, yeah, so. And some of them, actually currently, most of those people think that the best, most promising way to go about this is to look at the brain, at human and animal brains, because the brain actually works. And it's the only system that we know that is not digital and does real good computing. And I come to that later. So now I want to go back to material science at the Zernike campus. So this is currently fashionable. So how should I say, rising something. And lots of funding and lots of scientific interest behind it. And in the Zernike Institute, in particular, and in the materials research landscape internationally, neuromorphic computing has become the fashion of the day, if I may say so. I'm not a material scientist, but that's my feeling. So among those about 40 groups that we have in our Zernike Institute, 6 to 7 have shifted their research from whatever they were doing before with their materials to neuromorphic computing. So they are now looking at their strange materials, which can be carbon-based, electrical, magnetic, skyrmionic, whatever that is. All kinds of physical quantum effects are being analyzed in different substrates, and normally for different purposes. But about six groups, have now focused on trying to understand what can we do with these crazy things for new computing systems. So there's a lot of interest in the Zernike Institute. So that's one thing. And there is one person in the Zernike Institute who, in a sense, is the driving ultra power behind all of this. And if you hear the word CogniGron Center, and the person behind it is Beatrice Noguera. She is a theorist, and she has created, as far as I know, because that happened before I came here, but from what I learned and what I see, she is the driving force behind CogniGron. She's a natural scientist, a physicist by training, and she has totally switched to neuromorphic computing in her material science group. So how did this happen historically? How did the CogniGron Center start to exist? I wasn't here when it was, when the first roots were laid. I can only sort of tell you what I heard. And there's a big mystery around this. So the mystery is mysterious to the day. Namely, it must have happened, so I would guess about 5 years ago, that a very, very rich Groningen burger, so citizen, donated
an enormously large sum of money to the university. No normal mortal knows exactly how big this sum was, but we know how big it became after the university and the city of Groningen added their share to this, according to the contract with this person. The final outcome was 77 million euros. So that was a sum suddenly the university had that it didn't have before. And this donator, whose name is unknown still, so it's really a pretty kept secret, and he gave the university freedom to do with this money whatever they want, except it must not go into medical research. So, which is a very uncommon thing for large donations. Normally, it's exactly the other way around. So some old guy, very rich, is going to die from cancer, donates 50 million for cancer research. So that's the usual thing. And but here it's the other way around. This donation came earmarked to the charge to the university leadership, find a technologically relevant topic where there is a gap in research currently and where the University of Groningen could sort of showcase themselves in the Dutch and maybe European landscape to become a forerunner. And then there was, so I can only imagine, and there was a lot of power game behind the scenes, because I think many, how should I say, power researchers wanted to get a share of these 77 million. And so I wasn't here, so and in the end, Beatrice Noheda did win out, and this money was then turned into the CogniGron Center for basically that I will explain in more detail later. So, but the idea is material-based, non-digital, unconventional computing, where the material science expertise that we have in such a high concentration here, motivated ones on top, together with the Bernoulli Institute people who are theoreticians, modelers, computing people of all sorts. These two together, plus these 77 million, and call it CogniGron, and then become the star in the on the horizon or in the universe of this modern development of neuromorphic computing. So what was done with these 77 million? Because the Zenit Institute already existed and the Bernoulli Institute also. So what came on top? And on top came 12 new professorships that were created. That's quite a lot. Just 12 professors with permanent positions, so they are not temporary. The university, which is very uncommon, sort of agreed that they would post these as permanent positions. These 77 million sounds like a lot, but they will be eaten up at some time in a few years. And then the university has these 12 additional positions to pay for. So, so it's quite a commitment from the side of the university. So they did this, 12 positions plus 20 PhD positions. That's also quite a lot. And one administrator. There's no overhead. There is no office, no official secretary for the CogniGron Center. So if you want to contact them and have an official interplay with them, you will find nobody except Beatrice and Jasper van der Velde, who is the so-called scientific coordinator. He is in a sense, the manager of the whole thing. And one of these positions went to me. So I'm a very happy ultimate winner of this 77 million. Yeah. So that is in a sense, the brief history of this CogniGron. And what are they doing? So how do they operate? So one of the things that that they, yeah, so how should I explain this? What are they? Of course, they are doing research. They are funding research, they are funding these professorships, they are funding these PhDs positions, they are defining, you can sort of apply to CogniGron if you are some professor at this university and want to contribute. You can get a share of this money by getting one of these 20 PhD positions. You have to write a grant proposal. So all of this works, but this is not the real special way of how CogniGron funds. But the special way is connected to the special challenge. There is something that almost makes it impossible for a thing like CogniGron to work. And that's the deep clefts between different disciplines. So I don't know whether you're mostly Bernoullians, right? Although we sit here in biology building, so.
But mostly AI and CS.
Yeah, but it's
And yeah.
The cleft.
yeah. So we also have sort of subclefts in the Bernoulli Institute, and I don't know what happened, how the landscape looks like in the Dynamic Institute. But one of the main difficulties, if not the main difficulty, is that this from materials which are really hardcore physicists, they know their quantum mechanics because they always look at strange spatial interactions between atoms. And that's the mathematics of that is terrifying. And so there, you are one of those?
I mean, I've been getting more and more into it. I'm originally a theoretical physicist, but I'm moving more and more towards the ZM applied side.
Yeah.
And I have looked at what they do and gone, okay. It is, yes, it is quite hefty, especially like the whole thing with 2D materials and everything.
It's really advanced stuff from theoretical physics and modeling side. And we in the Bernoulli Institute, I would say there is not a single person who can really understand what any one of those in the Dynamic Institute is doing, and vice versa, unfortunately. So if you really want to have a real powerful development in the neuromorphic wider, I will say more about neuromorphic in more detail later, but now I want to just explain the difficulties that we have here and how we solve them. So you have to bring together theoretical nonlinear mathematics, dynamical systems, quantum mechanics, it's also part of theoretical physics. Then more applied material science, so people who really do these experiments, experimental material scientists, and then slowly going upwards in the ladder from the atoms to microchip design and technology, and especially unconventional devices. So this is other things like maybe you've got the memristors is also a fashionable thing these days. It's a non-traditional thing like a resistor, but different. And people think it's closer to something in the brain than a transistor is. So you need expertise on that, you could say, more applied end of materials research, microchip design, microchip technologies, architecture design of microchips, fabrication technologies. Because if you want to build prototypes, you must build them. And that's far from trivial to just fabricate demonstrators, small, of just coupling 20, 30, 100 or millions of little new things. How would you do this? You can't just put them together with a hammer. You need what they call a fab, so an industrial-sized production plant for microelectronics, and then you have to negotiate with them that they maybe help you to have one of their runs slightly in an unconventional way. And so And that is an expertise of an own sort that only few people have to just fabricate strange hardware at the nano, which is very structured at the nano level. Then it spreads out to people from robotics, so especially autonomous robotics, people who since 50 years try to understand how can one build little controllers that can help a little wheeled or armed or whatever machine to walk around and do its own decisions. So there is, maybe some of you know about this agent modeling. So what is an agent in the sense of artificial intelligence? And how can we implement learning in robotic hardware? Why are these people interesting for neuromorphic computing? Because they come closer to what a brain does than an abstract artificial intelligence researcher does. Because these roboticists, they connect to sensors and motive, must do that. And they are facing strict real-time constraints for their computational solutions, because the robot has a body that when it falls, falls, and it cannot just wait until it has computed what to do against the fall. It just must always deliver. All of these are properties that are not normally handled by classical algorithms. You need special types of algorithms, and they are closer to the brain. And if you want to learn from the brain, you need people who tell you what the brain does. And these roboticists are sitting, in a sense, close to neuroscience. They actually collaborate with neuroscientists, and especially with insect researchers. And on the one hand, and on the other hand, they are engineers who know how to program and to compute. So they are key players in this neuromorphic game. Then you have, of course, theoretical computer scientists of all sorts, and mathematicians, as I said already, dynamical systems, but you also need mathematicians from quarters, and more generally speaking, complex systems modelers. This is a brand of doing interdisciplinary mathematical physical work that has its own tradition. You need those people, or would need them. And what else do you need for that? Yeah, you need social scientists and psychologists and philosophers. Why? Why would you need those people? Don't be too haughty and condescending. You need philosophers, social scientists, sociologists.
I think philosophers, I know that there's a whole branch of philosophy that looks into like how to connect what we know now about different neurons to the actual how we act. Also, that's also guess where psychology comes in, right? Because you have to, like, we act, and that's just, and we can understand the human brain, but we can theorize about how the neural models that we have now generalize to the human brain. And
Yeah.
that's where these people come in.
Yes, that's one of the ways how they come in. So philosophers actually, there are some philosophers who are really tough researchers who maybe know more about formal logic than you do, or I do, and who also know more about mathematics sometimes. So there are amazing people among the philosophers. And they have a tradition to think about what is computing and what is also brains, what is consciousness. That's something that I have it, I don't know why. And so that's a topic I don't want to discuss. But these philosophers have a tradition of really deep thinking about what is information processing, thinking, reasoning, computing, what is the nature of brains versus what the brain does, so computing versus its material basis, and discussing these things with, if you are an engineer, AI person or so, and you really want to get into mental trouble, productive mental trouble, then you really start reading papers from those people or discussing with them, and you will feel that you're really challenged in your conceptions. And they are also needed for another reason, especially the social scientists and social philosophers, because if you, in the end, succeed in building brain-like, neural-like, strange new hardwares, then they will not be anything like the computers that we know. I will just briefly summarize in what strange ways those systems most predictably will be different. But to the extent that they are really like brains, they will be individual, so you cannot clone them. Computer you can buy too, and they are identical. Microchips have the identical input-output bitwise operation profile. These neither brains nor these microchips will have that for physical reasons. So there's no system that you buy later is, in a sense, entirely predictable what it will give you, and it will not be reproducible identically. You cannot just copy it, and you can't program it. It must be trained or shaped or formed or configured, but it can't be programmed. You can't just tell it, with a nice programming interface, do this, do this, do this, and then it will do that. So these things seem already pretty clear, yeah?
Could you explain that? That sounds so funky. Why they're not the same, or like why they can't be cloned? Or
yeah. So the reason is, actually there are several reasons. So, but one of the main reasons is the following: if you really want to come close to what the brain can do. No, I even start a bit earlier. So I start with politics. So one of the reasons why neuromorphic computing is currently receiving so much attention and also funding, not only in cloning. So similar things happen elsewhere. And also the big IT companies fund heavily in these strange things. So where does this interest come from? And there is one main selling story. Why should there this public interest and this public spending on this strange new way of doing crazy things that no one really can promise yet? And the main reason is energy efficiency. So whenever you read a public announcement from these fields or go to the homepage of CogniGron or read any paper in that field, you will always find a blah blah introduction where it says, oh, look at digital computing. They are wasting now or using about already 10 to 20% of the world energy budget. Oh, that's not sustainable. But look at the brain to do something for which we now need a server farm that burns megawatts, many, many megawatts of power. It can do the same thing even better with 20 watts. So if we could use insights from the brain, so I'm still reporting from the initial chapters in these papers, then we would have a world full of joyful computing at a very, very little energy budget. So that's roughly the story, which really sells neuromorphic computing. So you will not find a paper where this is not made this point. Okay, now I return slightly to your point. So if you really want to have extremely energy efficient systems, then there are certain physical basic laws. They must be very small. So the functionality, the complications, the computing, the bit handling, there will not be bits, but whatever is handled there cannot be handled in large chunks in large places. The closer you bring these things together, and the more nonlinear they get, and the more quantum close, the better in terms of energy efficiency. So that is something that is quite clear and has been clarified by complex systems researchers with a theoretical physics background. So there are even names for this. Maybe if you're interested, you can Google Landau limit, and then you or Landauer limit, and then you will find the theory behind this, and why small is energy efficient, and you can't get this with bits, so you can't make digital computers smaller and smaller and smaller and energy efficient, more and more and more energy efficient, because this already the limits of smallness are reached for technological reasons and for quantum mechanical reasons. So you will not be able to make microchip elements much smaller if you want to preserve clean bit operations, which you need for digital computing. So, and if you make things smaller, you lose precision because you come closer to the quantum world where energy is very efficient, but you also have noise, randomness, and you can't replicate the details of such circuits anymore. If you do the computing at the level of the interesting operations at the level of a few participating atoms, then there's no way to mass produce identical replicas of such systems. So they will just be similar, even if you try your very best to reproduce them as microchips identically, they will. And also later you cannot program them, that's a different story. If you could program them, they would be digital computers. So the fact that you know the computer can be programmed, has this nice interface, an editor, and that you can trace everything that's on it, that's directly connected to it being digital. So a non-digital analog computer cannot be programmed. So it's just not possible. It's just, there's no interface. There's no mathematics that would tell you how to do that. So the only thing that one can do with these new neuromorphic things is to train them, to shape them, to let them adapt themselves according to rules that the machine learners invent. And I'm a machine learner. That's how I was pulled into this whole field. So I forgot to name machine learners in this list of disciplines. So that's, yeah.
So there would be more like functions in a way then? Like single purpose functions in a sense then? Or
no, not functions. They would be dynamical systems, not functions. So if in the utmost mathematical abstractions you get dynamical systems, but stochastic ones and spatiotemporal ones. So I don't want to go into the math side, which is my hobby. I'm not so, but I want to come back to what does CogniGron do? So the mode of operation beyond the standard funding and project definition things. So one of the main challenges and of the main activities and the nicest activities are to help people from different disciplines to talk to each other. So so my background is first mathematics and then AI, robotics, and machine learning. But I'm not a physicist, unfortunately, and I was at some point some years ago pulled into this neuromorphic world, and then I met people who spoke a very different language from mine, totally different. And I didn't understand very much, and they use more acronyms than computer scientists. So it's really not easy. And it took me many years to even understand some basics of that field. It's not only the, you could say, the mathematical, technological detail that is different, that would take a big effort to understand. It's also the entire mindset. So maybe I can briefly relate what I learned. What is material scientists doing? How do their brains and their hearts operate? So the first thing that I don't understand at all when I first met them is the word that they use most. That's the word characterize. So does any one of you know what the material scientist means when they say we want to characterize this material? They were always saying this.
Make it have a characteristic.
Yeah. Characterize.
The behavior of the material in different conditions.
Yeah.
Just create something, this material.
No, so what you say is they just want to know if they have a new material that they just produced,
and put on a little slice. What does this do? How does it operate? At different temperatures, at different voltages, at different magnetic fields, at different ages, at different exposure to air, whatever. So there's a whole range of external conditions that you can change. And then, how does this system react with this material? And is it different if I have it in 3 layers of atoms versus 5 layers or 2 layers? And if I produce it with this method of production versus that method of production, is there a significant difference in behavior? And knowing all of this, measuring this means characterizing this. And now comes the thing that I did not understand in the beginning. So it's easy to understand that by characterizing they mean measuring these things, that they have these plots under this temperature, these temperature sensitivities, all that. So they later those plots at the end, and then they have characterized the material. What wasn't clear to me is that this is not just like what I used when I was a hobby tinkerer in electronics. If I wanted to measure a resistance, what do? You take a voltmeter or an ampere meter, put these 2 probes on the 2 sides of the resistor, and then you measure it. 20 ohms. So very easy. But if you want to measure the resistance of a 2 atom thick slice at a temperature of 0.3 Kelvin under a certain electric field, then how do you do that? Well, the first thing is you write a grant proposal. That's how you do it. Because you need new apparatuses in which you can actually carry out this stupid little measurement. And it needs to have a robot arm because you cannot just put these things with your clumsy fingers in there. You need to have a high precision manipulator that works under almost vacuum, close to Kelvin, and it must have observation probes that you can see what's happening there. Typically, some microscope is part of this thing. And then you must be able to do it, and you must be able to measure these voltages or whatever you want to measure there, which you can't use 10 volts as a measuring voltage, then the whole thing would just evaporate immediately because it's only a few atoms. So you need the most expensive precision measurement gear that money can buy, just in order to carry out one of these stupid measurements systematically. So, and if you have a nice new material that you think is very promising, what do you do then? So you write several grant proposals and hire a flock of good students, PhD students, and then you wait 3 to 4 years until you have those curves, because it just takes that amount of time. But to work in your new colleagues, to get the whole lab running, to replace spare parts if they break, which they do all the time. They have waiting times until then, and so forth and so forth. You can't imagine as computer scientists. Is anyone a mathematician here? Mathematicians can't imagine this even less. So what an enormous effort goes into just measuring or characterizing nanomaterials. So it's not just measuring, as you know it, fever or temperature outside or so. That's very clumsy. If you really want to measure these fine-grained, close to atom size phenomena, it's just always edge of what equipment can do. And therefore, the lab of Beatrice Noreda, when she first showed me around, so if you go to a lab, a robotic lab in Bernoulli-Bourg, for instance, Hamid Reza has a little robotic lab where he does his research with 2 robot arms. Maybe you have seen it or not. So what is the square meter size and the money involved in robotics lab? Square meters, 20. So, and money, well, it's a few 10,000
certainly. So when there is no header, showed me around first in the Zernike Institute in her lab. It was, first of all, just the square meters of her lab were, I don't know how many, but at least the whole floor size of an entire floor in the Bernoulli Institute. That's only one of the 40 groups in the Zernike Institute, full of apparatuses that looked very like fridges. So white boxes. And then she told me one of these boxes, what it costs, $500,000 if you buy it, and what it does. It measures some voltage under load. So, yeah.
Yeah, I mean, they also have these things standing there. Like I remember working on a project somewhere, and I was in a room, and I was told, don't touch that thing. It was just something standing around, because the machine that is standing around here costs $500,000. You know, just casually in a room that no one seemed to be using the thing either.
It's a different word, and that's what they, if they use the word characterize, they don't just mean take 2 probes and measure and be done after 10 minutes. They mean that's their life. That's all the energy, all the professional struggles, all the competition, all the maintenance of a large lab group who must work together well, all those PhD students, they must be trained. All of this is what they do for a living day in, day out. And they call it characterizing, that's what they do. And it's not clear to us, theoreticians, what that means in practice. Yeah?
So in a sense, characterizing is to material scientists what learning is to, what training is to machine learning.
Yeah, but it's so much more difficult and real-worldish difficult, because you really have to run a very complicated experimental setup with all the stuff that belongs to it. So these groups are also typically large. So if you see the group photos on the web pages of these material scientists, it's not just like in computer science, it's often 20, 30 people, one group, because it's a lot of PhD projects that go on concurrently. Yeah, so that's amazing. If you get into contact with these people, at some point you start realizing that we as theorists, we live on a very privileged and happy planet. If you have a good idea, you can maybe, if you're a good programmer, test it in a few days. A material scientist, just like a neuroscientist, by the way, there are striking similarities. They then have to have a planning horizon of years, and have to be able to strategically develop such a plan to actually make this happen, because they can't do it themselves. They must be just managers of a very complex infrastructure to make this happen. So this is one of the things, if you indulge into interdisciplinary research, and so just to conclude this piece of the story, this is also the mindset of experimental material scientists. They can publish all those curves, and everyone else in the field knows what goes into just coming up with the measurements for such a big graph. Then, so they are, how should I say, satisfied or happy or fulfilled if they can find new materials that have strange new curves. And if they then have also theoreticians in their group that can explain these things, they are super happy. But sort of and that's the normal end of scope for material scientists. That's what they are trained for the experimental side. And also trying to understand this mathematically as theoretical physicists. Why do I see these curves? Which is often super difficult and can only be done approximately. Is anyone taking my course in machine learning these days? Because I never see you in this stupid online scenario. Yeah, so the one method
that they use in understanding these measured curves is sampling methods. So I just want to run this in. Really, sampling is an important enabler of theoretical physics. You can confirm this.
What do you mean with sampling?
Yeah.
See, I'm in the material science field, right?
No, in theoretical physics, if you try to verify models of complex systems and you want to simulate them on your computer, the only way this can be done is normally by sampling methods. And so.
Yeah, I'm not in the computation.
This is an exam now, so.
No, yeah. Okay, so so back to CogniGron and what is doing CogniGron, how does it function outside the standard ways of functioning, and especially in order to foster interdisciplinary exchange, which is really difficult. It takes a long time to really make people talk to each other. So currently, so they have all kinds of seminars and invited guests and talks. But the one thing that currently really works wonders is a weekly, very short presentation series, where every Monday at 4 o'clock online, there is a presentation of one of the people from the wider CogniGron spectrum, who presents what she or he is doing in 15 minutes maximum, very briefly, plus a discussion, which is also normally just 15 to 20 minutes. So, and that's it, half an hour every week. In this half hour, so first of all, it's because it's short, the time investment to do this seems not so big. An hour is very different from half an hour. So if you have to schedule 1 hour in your day, at least if you are very busy, then this is a commitment. You really have to schedule it. And it's serious, and you don't like it. It takes real life time away from it. But half an hour is a little coffee break. So especially in the first half of the half hour, the first 15 minutes, is only 15 minutes. And 15 minutes, I mean, that's just a little break. And it doesn't commit you to anything to just link into this ongoing presentation. And the audience is always in the order of 35 to 40. So I think this is quite a lot for such a regular event. And in 15 minutes explanation time across wide disciplinary gaps, you cannot explain really what you're doing. Impossible. But if you go to these, and I invite you to do this, so I will just tell you how to get onto this list of invitees in a second. But if you do this week after week after week, you get something like a very fuzzy but also very high dimensional thinking space. You see, okay, there's a sort of people that do these, that seem to do these crazy things. And there are these mathematicians who I didn't understand, but they seem to be working with graphs. and so forth. So you get a spectrum of stuff that's being done here on campus, just around you. And all of these people are interested ultimately in the same thing, in these neuromorphic things. And in this way, you get a coordinate system. You don't understand the coordinates, but you know they exist. And you get a feeling of the challenges and the options of this field, and also of the nature of what contributions are here and what would be needed. So always on a very informal level, but it really opens your horizon. This is really working. So I was surprised, still am surprised, how well this works and how motivational this is. If you just hear these short presentations, almost never understand almost anything, but you see these persons and you hear the keywords, and 2 weeks later you hear the same keywords again. It's like in different contexts.
something is building up over the weeks. So the person who maintains the mailing list for inviting people is Jasper van der Velde. He is the scientific coordinator of CogniGron. If you Google him at the staff search mask at the main pages, Van der Velde, Jasper, and you can also find him if you go to the CogniGron pages directly, because he's the scientific director. Yes, if you mail him, he will just put you on the invitation email list, and then you can decide every Monday at 4 o'clock whether you just want to join that session or not. Okay. Yeah. So, by the way, timing for this, I could go on endlessly. So the question is, what are your expectations? What is your time budget?
Well, endless time is a bit much.
The room is booked until 5.
Mm-hmm.
Yeah, other than that, I feel if everyone is not feeling very tired, like this is pretty light and it has a good flow, so whatever you prefer as well.
Okay, I do a little bit more then, right? Is that okay? Okay, so yeah. So I think I will say more about CogniGron, this institute or this center. Yeah.
Can you tell us more about why the sudden interest in neuromorphic computing is increasing?
Yeah, the interest is actually that politicians are buying this main selling story that energy efficiency is at stake and important. There are other reasons why the big microchip manufacturers and IT companies, Google, Facebook, they all do neuromorphic research now, are interested in this. And the main reason is, another reason for the increasing interest in this is deep learning. Have you heard about deep learning? No. Really?
Okay.
And what's your job?
Yeah. I also have heard of it.
You are a theoretical physicist, yeah. So, so deep learning or neural networks in particular, or machine learning or AIs, in the last few years, about 5 to 10 years, there was a real breakthrough in AI technologies. Today it's called AI, called deep learning. Neural networks, if you use Google Translate or a photo classification system, a database for photos that you can sort by faces, and all of these things are now done by neural networks. And it's a major thrust in technology on the one hand. It's also major innovation in data analysis techniques in all sciences. So these neural network technologies are not only appearing on the surface of a browser now, they are also permeating basically all fields of science as a tool for analysis. So it's a super success story, which I will not sort of unravel in more detail here. It's really an amazing, super breathtaking, revolutionary, innovative, empowering thing. And it has the word neural inside. So it's neural networks, neural brains. Aha, we learned from the brain. So if we can do the same thing, and the real power, high-end deep learning methods use really a lot of computing power. So if you Google GPT-3, who knows GPT-3, has heard of it? Yeah, okay, so the ones who haven't, asked your friends, what is it? Google for it. It is infamous and famous at the same time. It's sort of a praised as the current most advanced and powerful machine learning system, and it's also known as the most energy intense one. In order to train the system, estimates about that $4 to $10 million had to be spent on the electricity bill. And so the internet companies, especially Google and Apple, they want to have more AI in their systems, but they're afraid of the energy costs. And therefore they go for special hardware that is tailored to neural network architectures, and especially ones that are a bit more like our neurons, namely spiking neural networks, whatever that is. So they're a bit further away from classical machine learning, closer to neuroscience, and have promises of even using less energy. And that's main reason, one other main reason why neuromorphic computing is currently so popular. And popular is the wrong word. Such a goal for funding, such a sinkhole for funding. Because we have this, you could say, the success story of deep learning has made decision makers believe that it might actually make sense to spend in this area. It's a proof that something goes in this domain. So people who try to do neuromorphic computing or materials-based or blah, blah, blah computing, such initiatives were always there. So there were always niches in computer science, very small niches populated by strange people who tried to come up with alternative ways of doing computing, non-digital, non-symbolic. But it never really catched. No funding, no successes, and these were, you could say, esoteric little niches. And this has changed because of the breakthroughs of deep learning that showed that going neural can actually change the world. Then the energy problem. And then there is a third factor, and that is the single device, the so-called memristor. This is another, it's just a little technological thing on the one hand. Who is familiar with what a memristor is or heard the concept? Yeah, so a memristor is a device like a diode, well, not exactly, but it's something that, like a capacitor or a induction, how do we call this in English? Inductor? Inductor, is that an English word for?
Yes, that is.
Okay. If you have a coil of copper wire, it's an inductor.
Yeah, yes.
That's an inductor. Okay. So there are resistors, capacitors, inductors as main, you could say, passive elements in electronics. And according to some mathematical theory from theoretical physicists, in principle there is a fourth thing of this sort, as elementary as these three, and that has been mathematically described as a system, as a device that is a mixture between a resistance and a capacitor. A capacitor is a dynamical system. If you put voltage in it, it sort of loads. By the way, an induction has similar properties. So it has a time course. And then if you connect it with a resistor, then it unloads its charge. So in order to understand what a capacitor is, you have to look at time sequences. And the memristor has been postulated on theoretical grounds to complete this trio by a fourth one, and then according to this theory it's complete, there are no more, as a system that, like a capacitor, has a temporary response to voltage in, loading, and later resistance of currents leaking. The memristor is also something that has a time terms of its resistance. So it can, in a sense, store resistance and give away the resistance later. And it's unclear whether you can actually build them.
No, they exist.
Yeah, that's.
I can just witness and talk about people using them.
Yeah, but so there are debates between the theorists and the engineers. So many people have fabricated devices, material scientists, that come close to this idea. And the question is whether you can only approximate this behavior by awkward tricks, because they are actually quite awful devices. That's what I say. And you would like to have them sort of realized by an elementary physical phenomenon, and that is something that so far no one has found, and it's unclear whether they exist actually on the very, you could say, basic level. But anyway, this memristor is mathematically elegant. On the one hand, it completes sort of the basic building blocks of electronics by a fourth thing, and it has been built since several methods have been invented by material scientists to actually build memristors. And now comes the thing that is making memristors to neuromorphic. If you look at memristors with a very generous abstraction eye, they look like synapses to you. So memristors and synapses, the connections between neurons, the trainable connections, there are some mathematical properties that are somehow related. And then, woohoo, you jump on the memristors and say, now we can build neural networks with these trainable connections in between the neurons, which is you could say the power source for machine learning, is that you train the synaptic connections. But so far, on these computers, you have to, if you want to adapt them and train them, you have to run very complicated formulas which just draw current and so energy. But if you could do these computations not in a von Neumann machine by numerically simulating the stuff but directly in one physical element, immediately in physics, that's in material, without any computation in a sense, automatically, directly at the place, then you have suddenly the idea that, okay, we can build learning neural networks that suddenly jump in energy efficiency by orders of magnitude. So, and this promise of memristor-based neural networks, where the synaptic connections are not any longer simulated numerically, just as numbers on your computer, but are directly in the microchip, little junctions between copper wires, so to speak, which really function like trainable synapses. That is a super promise, and that has sort of led to a to a boost of memristor research. I would say all over the place. So if you ask any one of these 6 groups here in the Zenit Institute who devote their research to memristor stuff, they will all try to, among other things, also build memristors and put them, make them easily fabricable, stable, and whatever, so good properties. And that's a current hope.
Does the role of electricity change with memristors in any ways?
The role of electricity?
Yeah, compared to the regular electronic components.
It's still electric circuitry that you get, if that's what you mean.
Well, I mean, is there a special, more, I don't know how to say this. Never mind. I'll think about it more. Maybe I get a better phrasing.
Yeah. So these neuromorphic and unconventional computing people, many of them, and the memristor people among them, stay in the world of electronics. So the chips that they want to build are still electronic chips, but others also work in other physical domains. Especially there's a field called optical computing, where the thing that does carry information so is not voltages or currents, it's light. That's the established field with its own historical tradition. And there are also people who try to do computation in chemicals, or even in oscillations, so in mechanical vibrations. That seems weird, because it connects back computing to the good old times when you had these cogwheels and so the first computing machines from Babbage and Co., they were mechanical engines. And now it seems totally outdated to think again about mechanics as a source of computational processes. But the material people have been courageous enough to actually do this, yeah.
Is there also research in whether what the lifetime or the life cycle of materials?
Oh yeah, that's a big topic. So membristors and other strange new materials, they have limited, they call it endurance. So if you try to have one of these membristors, and in the perfect world you could just use it, retrain it as often as you wish. But actually these things age. So you have a few thousand cycles of operation and then they get broken. They just lose quality. And this is inherent. The more small scale you get in your mechanisms that you want to exploit, the less long living are they.
And can you reuse them after, or is it just goes to waste?
Yeah, that is the research that has to be done. You cannot just reuse them. They change over time. But our brain also changes over time. And we have all kinds of very interesting learning and adaptation and recalibration methods to compensate for the loss of neurons that we all suffer from. So at a certain age, I don't know which ones, but I'm beyond that age. Every day in the morning when I wake up, I have fewer neurons than the day before. And I don't know when this happens, so maybe you should still feel on the safe side. So, but our brain doesn't suffer dramatically from it. So, and also if we drink a little bit, we still can speak up to a certain level. If you, however, would have additional computer and you just scratch a little bit on the brain microchip, you just take a needle and sketch on its surface, then your computer is certainly just waste. And it cannot recover from this. Any single dramatic injury will totally kill it. Whereas our brain is amazingly resistant to damage. Not totally, of course, but amazingly so. All sorts of damage. And we very quickly readapt. And such self-healing or self-calibration methods would be needed to be first better understood, so research in this, and then use them on the material level. So at the very micro level of potential materials, implement materials that are self-healing in a certain way. That would be one answer to this aging problem. So you see, this is one of many problems that are totally unsolved. I should at this point just stop, because now, in a sense, maybe you are positively curious about all of this. If I now would start, if I would now continue with the real difficulties, so then you would, in half an hour, you would leave this room like this.
But I think it's also fair, because just having the, well, optimistic with only half of the perspective is also not.
Yeah, so there are enormous difficulties. Progress is super slow. Yeah, and in many, many ways it's slow. And it's a foundational, fundamental research thing. And this is one of the main questions that I have, on the main dangers that I see, that the current interest, funding, spending, and enthusiasm in many quarters is based on hopes to quickly see something sparkling which will not be fulfilled. So and then so my fear is that we are now still at the rising part of such a hype curve, and we will not be able to deliver these systems anytime soon, because it's really a lot of fundamental questions that need still to be solved. Among others, understanding the brain. So you see, it will not happen that we will quickly have these systems, and that's what I'm afraid of. Yeah, but you shouldn't listen to me. You should.
Maybe a fun question.
Yeah.
Sorry.
Yeah.
I was just going to say that even if we were to assume to theoretically design those, because we said that they are not going to be trained the same way as like visual computers are, is there like any idea, even if highly theoretically, what the expected learning rate would be?
No. So we are currently at the very beginning. We have a few demonstrators, but they don't carry over to generally understood principles. No. So yeah.
I was wondering if you could talk a bit about your own research within the CogniGron and like how it connects.
Yes. Gladly so. So, but maybe.
I have a question about memristos, but the main question is, like you said, it's an electric component, so I assume it has an input and an output. But then, for example, transistors.
Well, it does not directly have an input and output. It has two sides, and you can run it either way. Yeah.
But like when I think of training, I think it has a certain value, and then I change that value. So I was wondering, like, and for that, you kind of need more than just two sides. So you have like a
sides are enough. Like a capacitor also has two sides only, and then you put the voltage in it, so then it charges, and then you, depending on how you close that loop, you can either charge it or decharge it. And the memristor is just a resistor, but one that has an interesting temporal behavior. So if you put voltage on these two sides, or current rather, then its resistance changes, and then if it then later is so it does not actively produce current. It's not a source of energy like a capacitor. You cannot store energy in it, but you can, in a sense, store resistance in it. And then if you later just have current flowing through it, resistance will change again.
Okay, so then, or if I wanted to build some system in the future, I would always need more components. So it wouldn't just be built out of memristor.
No, memristor alone is not enough. Yeah.
Okay.
Also, in our brain, we have more than only synapses.
Yeah, makes sense.
We also have the neurons after the synapses. Yeah, no. Yeah, I can quickly say my own research is it's machine learning is my background since 15 years. Recurrent neural networks, so neural networks that operate as dynamic systems. And in the last few years, I have become sort of theoretician for neuromorphic theory, mathematical theory. So going away from machine learning, my current research is about mathematical foundations to describe information processing in very abstract ways. In ways that are so abstract that they can cover digital computing and new forms of computing. So very abstract mathematics now. I'm a mathematician by training. Yeah, but I'm also an interdisciplinary person. So my main use for CogniGron is as a you could say communicator. So I know many people because I'm old. If you get old, you know people. And so among others, I was hired for networking and just talking to other people. And yeah, that also is a lot of fun. So I give many talks in different places and I try to create a network. So that's part of my professional life. not my direct research, but it's part of what I'm paying for. Yeah.
I was first. So, well, I have a bit of a fun question in the sense. So, assume that all the challenges will be taken on and they will all be proven doable, let's say, with neuromorphic computing and the memory systems. Where do you see this technology being used in the day-to-day life in like 40, 50 years or so? Like in our smartphones, or will it replace our computers? Will it be in our brains?
This is the question that everyone fears to hear. So it's unclear. So finding out what could this be useful for? If we would really have real brain-like behavior on chips, and what would you be doing with them? Because you cannot use them to replace your Excel files. Because Excel is something that needs to be reproducible and clean and reliable. You don't train each Excel file anew and then not be able to copy it, by the way. It's not possible to copy these things. You would only have your Excel file and it would degrade. So 10 days later, it would have forgotten something, but maybe have invented new stuff. So what would be use cases for such strange devices? And this is an important question, because if you want to apply for funding, one thing that the funding authorities always demand is that you demonstrate it's relevant for the economy of the country, of Europe, of the world, and so forth, blah, blah, blah. And then you have to be inventive. What would this be useful for? And this is a painful discussion because no one really knows. So there are a number of basic propositions. So the basic answers that you will get from people working in the field are the following. Such strange devices which combine cognitive brain-like ways of functioning with very low energy demands. They could be used in, and now I have a little list, the standard list that you get in these papers. So you have heard of edge computing, that there is an idea that in the future, sort of artificial intelligence and other clever computing stuff will move from central servers to the edge, that is to your wrist, to your smartphones, to wherever, to sensors, environmental sensing, to well, at the very periphery of the network, of the internet, so to speak. To little robots, little sensors in your home that do some monitoring or whatever. So you could say that the edge of computing world, and that much intelligence and complex processing should be done out there at the border to reality, and not in some central servers, because central servers mean, if you do all the interesting intelligence stuff centrally, means a lot of communication and data shuffling between the periphery and the center. So that's the idea of edge computing, and then there may be many functions out there at the edge that don't need the precision of an Excel file all the time. So especially so-called smart sensing and things where you want to have some reaction to some simple, or maybe not so simple, but maybe even not very well defined environmental stimuli. For instance, a sense in your house that sends a warning when it smells something strange. Either smells like fire or some gas or some toxic thing. You just want to have an alert that something smells not as it should. So that is a function that is something that animals are very good at, and that where there are models how you could do this with crazy hardware, with sensing crazy hardware. That's actually part of my own research. And you don't need high numerical replicable precision to do these computations. It's enough, and even in a sense better, if you use a noisy neural network for this. And so smart sensing at the edge is one of the answers that you get. If you ask the question, this nasty question, what is it good for? My feeling is that we don't understand the question yet, really. If we really would have the ability to build strange hardware that's a bit more brain-like, not as controllable as we are used to, not programmable, but maybe able to have a very much higher throughput of information. So the raw capacity of these things could be gigantic compared to what we have today at a low energy budget, but different kind, of the same kind as animals and humans in a sense. No one of us has really thought about this, what could we do with this? And new applications, new ways to interact with these technologies would probably arise from some crazy startups that have a bright idea and that we can't foresee. So probably my feeling is that we are currently too much still in our old ways of thinking about computing to really know what might happen there.
This sounds an awful lot like researchers were caught up with whether they can do it and have not thought about whether they should do it.
Yeah, and that is why we also want to have philosophers and social scientists directly in the game from the beginning. They are the ones who maybe have the better feeler, you could say, sensitivities to think about such questions. So a computer scientist is particularly badly equipped for thinking about how to work with things that are not computers. But a philosopher, another scientist, psychologist, they might be better equipped to think about this. And we are lacking this here in Groningen, in the CogniGron Center. We don't have philosophers or social scientists, but in network that's starting to begin to grow in the Netherlands, we do have contacts to such philosophers. Yeah, thanks. And so I'm still not finished with potential uses. So what you also get as standard, you asked this now, the question. So another answer that you get is in telecommunications. That is the answer that you get if you ask an optical neuromorphic computing person. So in optics, you have in principle much higher bandwidth or speeds of computing than in electronics. And therefore, in optical computing, there's a close connection to communication technologies. So the internet hard backbone. So the glass fiber cables, how they connect and how you can push large volumes of data through that. And for many sorts of data, you don't need total bit precision. So if you do video streaming, if some bits sometimes are a little bit different shade of blue than what was sent to you, no one will recognize. So there may be options for, let's say, mass throughput of gigantic amounts of information at, you could say, a less precise way than we currently have it in our digital infrastructure, where we demand ultimately perfect reconstruction of the input bit sequence. And if we don't demand this, then the optical computing people are starting to think about neuromorphic inspired communication links that do the routing and the header recognition and these things, the operations that are needed on the internet in noisy ways, but much faster to enable much higher throughput. That's another answer that you would get from the optics people. And then there are the people who, the deep learning people from Google and consort, they would say, okay, we want to have real intelligence, strong AI the actual real cognition ultimately running, and we don't want to burn an entire server farm whenever we recognize a picture. So that is another selling application vision. So the high end, the cognitive end. And my feeling is we don't really have a good understanding yet. We have no demonstrators of such systems, actually not we have a few ones, but they are not very sparkling. And then we haven't played with these yet, and we have no experience with them, and therefore I would say it's a bit too early to really know what will happen. So there were.
Yeah, you mentioned dynamical systems, and you're inventor of echo-state networks. So do you think that neuromorphic reservoir computing is promising?
Yes, as an intermediate first step. In the long run, no, it's too simple.
Oh.
That's another story. So I will not start to open this. This is part of my own history and background, and that would I normally talk about in an entire tutorial of 6 hours. So I don't feel like not starting that. Yeah.
Yes, I have another like question on the nature of consciousness. Our views of, I think, the nature of consciousness that will allow for consciousness to creep in into non-linear dynamical systems. And I'm just curious if you fear or hope or suspect that the lights might just come on in these chips if they are in large enough quantities oscillating at certain frequencies, or what your thoughts are about it.
My thoughts are, so as regards to consciousness, which is a topic that sometimes pops up in artificial intelligence research, I think, and philosophy of artificial intelligence. It's sometimes called philosophy of mind. I just stay away from that field. So when I was young, your age, I thought about this. And I read a little bit the philosophy of the day about these topics, and I found it extremely confusing. And I have a very simple model of that. My model of consciousness is that that is one of the things that we will never understand. And so once you have this decision, there is no way. Then you just don't bother anymore. So I really don't understand consciousness. It's a miracle. It's a riddle, and it's there, but there's no mathematical definition, and there's no experiments really that I would think you can use. So I just leave this out. So you must talk to someone else if you want to have consciousness stuff.
You talked about the mechanical computing. Does it also happen here in Groningen?
No. So just maybe that's a good ending point. Mechanical computing sounds strange, but what they do is maybe less strange if you hear a little bit more about it. You can use current microchip manufacturing technologies to actually etch little, they're called nanobeams, so little bars of silicon that are suspended, very thin, very nanoscale, very small, that are suspended between two hooks or whatever supports, and many of them. And then you have a nanoscale system of interconnected vibrators, so to speak. These nanobeams can oscillate mechanically. So just like a string on a guitar. But these strings are very, very small, a few nano something, and thick even thinner. So, and what can you do with them? You can excite them. They start to oscillate mechanically. They are excited electrically. So, and by interacting, by mechanical coupling, strange oscillation patterns can emerge in this network of interconnected you could say guitar strings, all mechanical, well, a bit electromechanical, because in order to excite them you need electricity. That is the way it's done today. And there are two fun things about this that I find remarkable. One thing is that this is extremely low energy, these oscillations. Just to have a little bit of vibrating in a beam of silicon is just, it's for some reason not eating much energy. Maybe it's the same as so I don't know. I would suppose, like with a guitar string, if you just strike it, it just oscillates some time.
There's resonance.
It's a resonance frequency that you get. Maybe that's the reason why it's not so much energy burned in this way. And the frequency by which they resonate is gigantic. So it's not a frequency like a guitar string. I don't know the frequency. It's certainly megahertz, maybe gigahertz. So it's very, very fast. And you can imagine that you might get interesting nonlinear behavior, mechanical nonlinear behavior, that is energy saving and can do interesting things. And what it has been used for is reservoir computing, for the ones who have heard this version. So demonstrators have been built by which you can do some signal processing. And strange things exist under the sun. Yeah, these could be also interesting sensors for motion sensors. Actually, the group that does this comes from motion sensing devices.
Where is it done?
In Canada, and the person who does it is so I have not enough neurons to memorize all those names. I forget them immediately. If you send me an email, I can quickly look it up. I know where to look for the name, but it doesn't come to my mind right now. It's a French name. It's in the French part of Canada. I think it starts with L. That's the
Laplace.
Yeah, so I'm a bit tired because I have a lecture before, or a tutorial rather. And so if you ask me, I would call it a day for this kind of thing. If you find this interesting, I can recommend you write an email to Jasper, and it's not committing you to anything. You can just, if you have time at Mondays at 4, just dial in and see how it feels if you get your exposure to this strange world. Yeah, so computing. I need a good final bottom message. So I'm pretty sure that there are more ways of doing computing than with the classical Turing machine, but we don't understand this yet. And this is for computer scientists and mathematicians a real wonderful challenge. So at least I think so. Yeah.
Thank you very much.
Yeah, you're welcome.
Thanks.
Thank you.
So I'm amazed how many came here. So that's great.
Yeah, the capacity is 36 even. But, yeah.
So it's great to see real people again.
Do you know how much like Neuromorphic came from?
Yes, a lot.
Because I know they do like
Yeah, but it's also recorded. Wait,